In here, number two, a hot solution containing 1,000 kilograms of magnesium sulfate and water having concentration of 30% magnesium sulfate is cooled to 15.6 degrees Celsius, where magnesium sulfate, heptahydrate are precipitated. So you can see in here that it is hydrated crystals. So calculate the yield of crystals in kilograms for the following cases. Letter A, assume that no water is evaporated. And then letter B, assume that 5% of the original water in the system evaporates on cooling. So in this case, you're given 30% feed concentration as opposed to the one in here where you're given basically a solubility. So let's try to draw first. So for the given, what you have here is the crystallizer, and then the feed, and then of course the solvent, the vapor, and then in here what separates is the mother liquor and the crystal. You have here the M. You want to label this. So what are the given? The feed is given to be 30%. So I can say that this is. And then what else is given? But you don't know the crystals. Cooled to 15.6 degrees Celsius. Okay. So I can see that, as I have said earlier, the temperature of the magma is the temperature of the mother liquor, is the temperature of your crystals, which is 15.6 degrees Celsius. Can you please convert this to Fahrenheit for me? 60.08 degrees Fahrenheit. So why did they have to ask you to convert that first to degrees Fahrenheit? Because you know that the crystals come out at that temperature. So it would be best to convert that because look at this. At 60 degrees Celsius, what is the composition of the crystals at that point? At 60 degrees Fahrenheit, let's use this, and then it would come out there. So I can see that here, the XL, the composition of the mother liquor, would be 0.245 roughly. Okay, so that's 0.245. So we will be using that in here from magnesium sulfate water phase diagram. So I can see that at temperature is 80 degrees Fahrenheit. The XL is 0.245 magnesium sulfate. And then you will notice here that the line that it touches is magnesium sulfate heptahydrate. So Mg SO4 7H2O, right? Okay. So why are these important? Again, you know F and XF. You don't know the XL. You don't know the XC yet. This one, by the way, this is XF. We have to know the XL. We have to know the C, right? How do we get the XC? XC is basically, as I said earlier, that's the molecular weight of MgSO4 for every molecular weight of MgSO4 7 hydrate. Can you please solve for the magnesium sulfate molecular weight and the molecular weight of the hydrate, please. It's 24.31 plus sulfur is 32 plus oxygen is 16 times 4 over all of these 24.31 plus 32 plus 4 times 16 plus 7 of water. So 7 times 18. So can you please give me XC? 0.4884. So let's just label them so we know where to look. 0.245 from the diagram, 0.4884. So that all the givens are here. And then what's being asked? Yield of crystals. So again, C. Then assuming that no water is being evaporated. So here, required, letter A, yield of crystals, or V is 0. And then letter B, the yield of crystals, assume that 5% of the original water is evaporated. Yield of crystals, where V is non-zero, it's 5% of water in the feed. Okay? So let's solve. Letter A. We have the overall material balances. So again, for the overall material balances, we know that F is equal to V plus L plus C, the feed. What was the feed? 1,000 kilograms of magnesium sulfate. So I forgot to place it here. 1,000 kilograms of the feed. So this is 1,000. And then if assuming this is 0, that means the L plus C will be left for me because L and C I was not given anything. So this is your equation number 1. And then what else? So for the component balance or the solute balance, I can see that F XF is equal to L XL plus C. Let's see. This one is given. XF, we know that that's 30%, so zero point 0.3. We don't know what L is, but we know that XL is 0.245. And then we don't know what C is, but X is 0.4884. So let's call this equation number equation A because that's specific to letter A. 1 and A. What is L? What is C, please? L is 774.03, and then C is 225.97, and then both are in kilograms. So you're asked to solve for the yield. So approximately 226 kilograms of what's the crystal per 1,000 kilograms of feed. This is your answer for letter A. Now, let's go to letter B. Again, overall material balance would be the same. Nothing changed. 1,000 is equal to V plus L plus C. Only that the V is no longer equal to 0. We have to take note that what it says in here is that 5% of the original water in the feed. So V, 5% of water in the feed. The thing is, the feed consists of 0.30 of the solution, which is the in here, 30% of magnesium sulfate, and then the rest is water. So that means this one, magnesium sulfate, zero point 0.7 would therefore be water. So here, I can see that this one is simply, this is 5% of the water in the feed plus L plus C. So 100, guys, minus, what's 5% of, is it 35? So 1000, this is 35 plus L plus C. Therefore, 965 is equal to L plus C. This is your equation number 2. And then let's go to the solute balances or component balances. For the component balances, 1000 times XF, which is 0.30, is equal to um, L, it's L plus CXC. What's L? We don't know yet. What's XL in here? 0.245 plus C, and then the XC is 0.4884. Now, I have a question, guys. What happened to VXV? Why is VXV not present in the component balance? Because there are no solids in the evaporated water. It's purely water. There's no solute. So this is what I call now my equation B. So 2 and B, you'll have your L and you'll have your C. What's the L, please? Can you please solve? L is 703.8, and then the other one is 261.20. This is kilograms, that's kilograms. So you're being asked to solve for the crystals formed. The yield is 261 kilograms of crystals per 1000 kilograms of feed. So this is your answer. Setting this up is the tricky part. You have to know the parts, you have to know what you need, you have to know if there would be conversions required so that all the data can be obtained. Like, if this, sorry, this one is not 80, that's 60.08.